Welcome back, Math 170. We're looking at the last section in Chapter 2, 2.9, Linearization and Differentials. So I'm going to start off by relating everything back to our classic finding the equation of a tangent line problem. But I'm going to start to use a little bit more generic instead of concrete numbers. So remember, with this nice problem, we have ourselves the need to find the point of tangency. So, or actually, I say we should address it. So point of tangency at this point, they are addressing this as A, and then the function evaluated at A. So it's the X value and the Y value. We also are looking for the slope of the tangent. And we do not have an actual expression or formula for our function, but we do know the slope of the tangent can be found by calculating the derivative of the function and evaluating that at A. So we're kind of reviewing back to what we've been working on. So if we were to then create the equation for the tangent line, I'm going back to look at point slope form. So I kind of like to write the algebraic form just so that we see. If I was going to now substitute in my actual values, I'm going to see y minus the y1 would be f of a equals, the slope is f prime a times x minus the x1 in this case would be a. Now remember, with anytime we're using the point slope form, a lot of times we really like to see the equation in slope-intercept form. So that can be done by solving for y. And when you solve for y, you are adding f of a to each side. So that is going to lead us to y equals f prime a times x minus a plus f of a. And what this really is just an equation of a tangent line. If you look back and kind of relate it, we have y equals m times x plus b. In a way, I realize you'd have to distribute in order to actually find the b, but that's what we're trying to get at. So I'll erase that for now, just so I don't cause any confusion. And this is what it means to find the linearization of a function f at the point x equals a. So if you can recognize where they are talking about L, capital L stands for linearization. And we now see they just wrote it slightly differently, but what we're looking at, again, is the equation of a tangent line. This time they put the f of a first. Sometimes that causes less confusion if we're doing the computations. So I still want to point out there's nothing different. We're still dealing with a tangent line. So try not to get too tied up in memorizing formulas. You can derive it just by knowing the concepts we've already been working on. So we go a little further. Sometimes when they define the definition, it doesn't work for all values of x. It only works for values of x near a. And then the question would be, well, why? Why are we allowed to approximate f with this particular formula? So let me do a picture again. A lot of times it helps to bring back analytical geometry to help us see everything. I prefer drawing things myself to get an idea of what I'm looking for. So if we can try our best to draw a somewhat curvy function f. And we're looking at a couple of things. We'll look at, well, what's the equation of the tangent line or the drawing of the tangent line? So I'll look at it maybe about here. Here's my A. And again, if you were to find the equation of the tangent line, remember you would have to find a point on the line that would give us our y value. And then here, if I'm drawing the tangent line, I'm trying to use a straight edge the best I can. Okay. So now we're going to address the near part. So I'm going to look at a plus h. H is always considered the small value. And we're going to exaggerate just a little bit because it does, we need to see it. So I need to make it a little further away. So I have this a adding a distance h. And there's a couple of things you could kind of play with. You can look at evaluating the function at f of a plus h. So that's what we have here. Let me draw that again a little nicer. And then we could also look at the linearization. So the linearization is looking at the tangent line. So if we're looking at the linearization of a plus h, I want to kind of draw that. We're still at a plus h. We would be looking at what's happening on the tangent line and then kind of going to look at its value. So it's L of a plus h. What's happening on the tangent line a little bit further away from A. And if you could see this, I'll try my best to highlight it. See if I can. Maybe I'll do this in yellow. The difference between those 2 points, f of a plus h and the limit, or well, I should say the linearization of a plus h, that distance right there, I'm going to venture to say that these values are not too far away from each other. And again, if you're kind of looking at it, there's a either when you're looking at it, the difference between the 2 functions or the difference between the 2 y values, again, you know, this linearization of a plus h and the function evaluated at a plus h, it's pretty darn close. Those are my comments there. Now, of course, I blew this up a bit so that we could visualize how this works. If we're moving everything down to scale, remember h is relatively small. So again, that's the near part. So there's kind of a picture to help us understand why are we allowed to approximate the function with its linearization. So we're going to look at an example to apply this so you can kind of see how everything works. Look at example 2. We're using a linearization to approximate the 4th root of 16.12. And yes, I realize we can punch this in on our calculator, everything's great, but we're trying to understand the concept behind what's actually going on. So when I try to approach problems like this, see if I can widen out the page a little bit. There we go. The first thing I want to do is try to choose a function whose derivative that's it's easier for you to find, or I should just say you can find the derivative. And the function that you find, it should yield a value that's pretty darn close to what we're supposed to be approximating. So that's the first step for us to kind of approach this. If we're playing around we want to name who would be that function. So choose a function. So you want to have it differentiable, and it's supposed to yield a value close to what we're supposed to approximate. So a lot of times if we're looking at a certain expression, right away what's blaring in my mind, I'm seeing a fourth root. So I can actually do this. I'll say let f of x equal, I'm going to use the same sort of format of what the original approximation is supposed to be. And if I'm trying to understand, well, I need to choose something. I think I can find the derivative of this. I have to have it in terms of x. So let's go with this. And I don't think I need to highlight it in orange. Let's just keep that. F of x equals fourth root of x. And make sure when you choose the function, it's relatively easy to approximate at a value that's very close to what we're trying to approximate in the first place. So if I'm seeing a fourth root, I probably want to pick a value that is quickly evaluated. So if this is the case, I might look at, let's look at f of well, 16 kind of comes to mind. So when you evaluate the function you've chosen at 16, that's fourth root of 16, and that's very quick. We can actually find the value is 2. So we know we can differentiate it, and we know that we can evaluate a value that's pretty close. That's the near part. 16 is close to 16.12. So now that that is the case, kind of keep in mind what we're trying to find here. Again, they're saying linearization. So it's not a bad idea to kind of write maybe the linearization up on the side to know what components you're trying to find. So we have linearization of x. That's the f of a plus f prime a times x minus a. So kind of think about it. Well, if we want to try to play with this function, I want to be able to find f of a, and I think I have that already. I've been playing around. I also want to maybe find the derivative of my particular function. So that's the second thing we want to play with. Let's calculate that derivative. Okay, so we're going to look at f prime x. Maybe before we calculate the derivative, anytime we see that radical, it might be more convenient for you to rewrite this as x. Remember, it's a rational exponent. So what is that? X to the 1/4? Just reminding yourself, this is not the derivative yet. This is you rewriting it. So if we were to calculate the derivative, we're bringing the 1/4 around. We're subtracting off 1 from 1/4. So 1/4 minus 1 is -3/4. And if we know we have to evaluate this, because I'm kind of seeing the f prime a come up, it might be to our benefit to rewrite it so that we have not only positive exponents on the x, but having the root radical notation back. So I'm going to rewrite this. It looks like we have 1/4. And then if we convert, the index will be 4, and we will have x to the 3rd. Maybe I'll center that one just because I like things pretty. There we go. So kind of what I'm trying to get at is I'm looking at how can I find this piece, and I'm going to highlight it in teal. So I'm on my way to finding this piece. I just need to calculate it at the value that I've chosen. So remember, when we kind of played with our chosen value, we decided that we were going to let a equal 16. So 16 is close to 16.12. Therefore, A should be about 16. That's our choice. So that's about the next thing I want to do within this process. I'm looking at f prime of A. And we're all pros at plugging things in now, but it doesn't hurt to try to show what's happening. A little bit of algebra coming back for kind of playing with some of this radical notation. When we do have an exponent on the inside of a radical and we only have purely factors, you can rewrite it so that maybe it's easier to take the 4th root of 16 and then take the power of 3. Very useful. So the 4th root of 16, my friends, we figured out it was 2. So then if we calculate this, 4 times 2 cubed, 2 cubed is 8, 4 times 8 is 32, so we have 1 over 32. That's going to be the slope for us. So let's see if we can now try to bring it back to this formula, this linearization formula. So number one, when I do look at this linearization formula, I want to plug in all the components, and I have to make sure I don't confuse my A's and my X's. That tends to be a little bit rough for some of us. So let's kind of make sure, give you kind of a third step. We're finding the linearization. At A equals 16. So if that is the case, the linearization of X is equal to f of A, and again, A was 16, plus f prime of A. In this case, this was also f prime of 16 times x minus 16. And again, remembering, we plugged in A to the linearization, not X. So be careful, we tend to get confused. So now we kind of look at the two components we just calculated. We calculated f of 16 already. So we have linearization of X. F of 16 was calculated to be 2. The derivative of the function that we chose, evaluated at 16, was approximated, or not approximated, but able to be written as the slope. We have the 1 over 32. And then we still have this x minus 16, x minus a part. Kind of highlight that so that we see. So we're just trying to make sure that the value of a we chose, and then calculating the function evaluated at a and the derivative of the chosen function evaluated at a gets substituted back in to the linearization formula. So now we have a much nicer formula. This is something that we're going to be using. Now we're going to utilize this, if it will let me. I'd like to box it so that we see this. So we are almost done. The last thing they asked us to do, we have to deal with approximating. So remember, with the approximation, step 4, I'll say, my idea is since 16.12 is near 16, this is value of x close to a. So this is kind of my approximation, or why I'm dealing with this. Again, I emphasize the near part. Then we could say, according to the definition, that the function evaluated at 16.12 is approximately equal to the linearization evaluated at 16.12. So if we're going to do this, now remember, you can't just calculate the fourth root of 16.12 in your mind. I know we can do this with a calculator. We then kind of look at what this means when we are using the formula that we derived above. So I'm going to highlight this just to make sure. And just so that we see this time around, we are plugging in 16.12. So this is where you're plugging in for x. So my friends, the fourth root of 16.12 can be approximated at the linearization of 16.12. And the formula that we found for that is equal to 2 plus 1 over 32. And then instead of using x, I'm using 16.12 minus 16. So again, just emphasizing one more time, we are substituting in for x. See if I can highlight that. Now it turns orange. So now what we can do ourselves, we just do a little bit of math. I mean, we may need a calculator for this, for some of it. I know we can go with this. Let me clean it up a little bit. 16.12 minus 16, I believe we get 0.12 back. Now this is probably where we do use a calculator. I don't waste your time. 1 over 32 times 0.112. Then adding 2, we should get 2.00375. And so this is the approximation. So let's see. How close did we really get? Let me go back. Let's pull up our TI and let's ask. What's the actual? What's the actual value of fourth root of 16.12? Let's find out. Pull up our TI. This is where I go back to my regular calculating screen. And if you want to evaluate a fourth root more than one way, you could go to a couple of things, depending on what type of calculator you have. Sometimes you have to press the root first, then you press the math menu, and then that would be the number 5 X root key. That's where the 16.12 comes in. Might look a little different if you have a TI-83 or so. And if you don't want to deal with radicals, a lot of times if you know the conversion, you could also have played with it using a rational exponent. So that would be 1 divided by 4. If I were you, and if your calculator is not showing a nice exponent form, a lot of times the TI-83s have this issue. Always include the parentheses around the fraction so it doesn't get confused. But normally if you're using a TI-84 plus or above, it will calculate it just fine. You'll see the actual math notation for you. So let's look. Compare back. I have a short memory, so I have to go back and check. Is this close? Go back. Look at our screen again. And yes. So just so that we know the actual value of fourth root of 16.12, using our TI, I'll try to write everything down so we see it. 2.003739499. So we're pretty close. In fact, we're pretty close to about 4 decimal places, so not bad. So just something to kind of think about. And I get it. It's fine if you're using your calculator to find values. There is a reason why they kind of make you go through this route. You may not see it in this particular course, unfortunately. So it kind of seems a little disconnected from what we've been studying already. But I just kind of want to bring back into mind that when you're looking for the linearization, you are really connecting it back to the slope of a tangent line. So if that kind of helps with the formulas and approximating, that's fine. I tend to see a little bit of a linearization differential that we're going to talk about. I see it more in Calculus 2. I believe it's when you're calculating lengths of curves and maybe sometimes it's surface areas of stuff. So when you see it, maybe you'll appreciate it a little bit more then. Maybe you appreciate it now. We'll see. So let's get more exciting. Let's look at example 3. I'm looking at using a linear approximation to estimate the sine of 1 degree. And it may be hard to see, but just kind of keep in mind, it is a degree symbol. And we already kind of spoke about how usually calculus and degrees, they don't get along. So we'd say why? Well, a lot of people like to think in degrees. It's easier for them to picture what's happening or where they're at in relation to the angle of the circle. But let's go with it. We'll see how this works. So the first thing, we're going to go back to kind of our process. The first thing is to try to find a function pretty close to what you're trying to approximate. So right away, the sine kind of throws me another idea. So I'm going to say, okay, that's f of x. How about f of x equals sine x? That's pretty nice for me to differentiate. And I'd probably be able to find some exact values. So let's find something pretty close. Something close to 1 degree. Be careful if you're in degrees. Some of you might like jump to say, oh, I know 1. 1 is really close. But when you look at the sine of 1, that is a lot different than how it affects the idea with degrees. If you're actually looking at what's the measurement of 1 degree, I should have a picture, but remember, 1 degree, if I'm trying to, it's very, very small. I mean, this is more than 1 degree that I see here. Remember, if you're looking at the sine of 90 degrees, we have a right angle. The sine of 180 degrees, that's a straight line. And what does that mean? 180 degrees, that's pi. And what's pi approximately equal to? 3.14, yeah. And then if we have here, we have pi over 2. So if we're dividing 3.14 divided by 2, we have approximately 1.57. So 1 degree is, really, really close to the x-axis if we were trying to describe this. So the value that we want to choose, I believe that choosing A equals 0 degrees is going to give us something closer to the 1 degree. So not 1, but 0 degrees. And there are other values that are close to 1 degree, but I only know how to calculate sines of special angles. So I had to choose one of them. 0, pi over 6, what else? Pi over 3, pi over 4, pi over 2. The closest one I can deal with is 0. So let's go with it. So if that is the case, we can evaluate. We have f of a. So f of a is sine of 0 degrees. Let me change that so you can see what I'm doing. Okay, let's look at this a little carefully. What is the sine of 0? That's the y value at the location of where you're on the x-axis. So the sine of 0 is equal to 0. So we have f of a equals 0. Okay. Now remember, what are we trying to do again? We're trying to find a linear approximation. So this is, again, you'll take the linear approximation or formula. Not a bad idea to write out on the side what it is. Just so that you know, you're trying to find each component of it. So right now, we've just calculated f of a. Now the next thing I'm looking for, maybe I'm going to look for calculating the derivative at a. But before I can calculate the derivative at a, I actually have to find the derivative of the function. And sine is nice. Derivative of sine of x is cosine of x. Wonderful. So now again, if we are trying to evaluate the derivative at a, in our case, a was 0, we have the cosine of 0 degrees. And the cosine is of 0, we're on the x-axis, right on the unit circle. The cosine of 0 is equal to 1. That's not too bad. So we could kind of look at when we're playing with step 3, you're trying to find the linearization. So we're finding the linearization at x equals a. Okay, so we are trying to say, let's plug in what we know. So let's go with that. I'm going to look at L of x. Now, do we know f of a? We do. That is f of 0. So that is equal to, and actually before I do that, maybe I'll help. Sometimes you have to see maybe some generic formula first. So see if I can do this for ourselves. Why isn't it letting me write? No? Aha. Okay, so remember, what happens at a? In our case, it's a equals 0. But I do like to maybe highlight it for you all. Here I am speaking at a equals 0, but I'm writing a again. Here we go. So a equals, let me see if I can do this a little bit more. A equals 0. My apologies. There we go. Okay, so if a is 0, we have this. A is 0 and x minus 0. So it kind of makes it a little prettier for us. So now, if we can, what was f of 0 one more time? Let me go back. That was f of a. So f of 0 is 0. Plugging that in. F prime 0 is 1. And x minus 0 is still x. So now we have ourselves a much nicer formula. And actually, let's clean it up. Again, here I am. I'm really obsessed with a today, I guess. So again, x minus 0 is just x. I'll write it down just so that we see it one more time. Clean it up a little bit. We don't have to worry about 0. 1 times x, that's all we have, x. So L of x equals x, super nice to approximate. So now we're going to have to think about this. If we want to play with this, we have to kind of be careful about what we're dealing with. I want to play around with the fact that we're looking at degrees, and we kind of have to be careful about what we're plugging in, because remember, we're looking at the sine of 1 degree versus the sine of 1. It's a lot different. So let me kind of give you some idea. We're looking kind of where we're at with step 4. So what is near 0? So remember, if we look at sine of 1 degree, we need to find something close. In my idea, I'm going to have an issue if I try to use 1 degree. So let's think about radians. So remember, 1 degree, a little off to the side. 1 degree equals pi over 180 radians. Just a kind of nice little trig review there. So sine of 1 degree is the same as sine of pi over 180. And that can be approximated by our function. So remember, we have to be careful when we're using degrees versus radians. Calculus, again, agrees with radians. So what I have, just so that we have here, since pi over 180 radians, okay, kind of keep this in mind, is near 0 radians, this is where we can do the approximation. Our function can be approximated by our linearization. So what does that mean? What was our function again? Our function was sine of x can be approximated with the linearization of x. So if we look at sine of pi over 180, we can approximate it with, again, the linearization of x is x. So in this case, it'd be x. And I should be a little bit more, let me give you another step just in case. Sometimes maybe we don't see that jump. So sine of x is approximated by the linearization of x. And then sine of x, what was the linearization of x? It was x. So if you're playing around, just so that we see this, sine of pi over 180 is approximately equal to what's linearization of x? Linearization of pi over 180 is pi over 180. Interesting. And if you actually are going to approximate it, we'd have to kind of use our calculators, of course. If I were to type in pi divided by 180, I'll give you a few decimal places. What is that? 0.017453. There's a few more. I'll just write everything in my calculator. So either version works, the approximation. And if you're actually interested, little note, maybe if we wanted to find the actual value, which is sine of 1 degree, for those of you curious, let's find out what it is. Let's pull up our TI. And I have to be careful. I have to figure where my mode is before I start pressing sines and cosines and stuff. And right now my mode was in radians. So I press mode. I'm gonna have to change it to degrees so I can actually see what's going on. Now I can go back to my home screen and I have the sine of 1. Not 11, the sine of 1. Let's see what we get. And let's compare it to what we have. And we should have sine of 1 degree is equal to 0.017452. And there's more to this. I realize I just can't see it at the moment, but I'm kind of just comparing. Look what we figured out. That's kind of nice. That's about 5 decimal places that they have accuracy to. So nice on the linearization. So again, if you get a little tied up, if again when you're playing with trig functions, be careful. It is a lot nicer to try to convert everything to radians so that you could fully understand this. Calculus and degrees don't necessarily get along, so be very careful. Having said that, you have a little chance to play with your homework a bit, to kind of really hone in on what it means to calculate it. And again, one more time, one last thing, linearization is really calculating the slope of the tangent line. So almost there. One other concept that we'll be utilizing usually a lot when you have differential equations, and we tend to use this a lot more a little bit later, sometimes with the integrals and maybe calculus too. It tends to be a little bit of a mind switch, going from what we've been taught already to now switching a little bit of what's happening. So, so far, I just want to kind of mention, we've been conditioned to think of this dy dx expression as a single quantity. But what happens, if you see the picture below, you kind of be able to describe it. You can kind of relate it to separable, two very small quantities. And so separable just means we can take the dy, whatever that might be, separate it from the dx, kind of like how we work with fractions. And if we do that, we're multiplying by dx on both sides, you'll get an expression or a formula for the differential. So this right here that we have is the differential dy. And if you want to see a picture of it, kind of helps us understand. And sometimes if you have a calculation of derivative at a certain point, you're actually finding the slope of the tangent line. So if you kind of relate slope to change in y over change in x, dy dx is very similar. It's kind of the same idea. There are some subtleties, but we don't have to go into it as much in this class. So let me see. I'm drawing a nice curved function, f, and just so that you guys get an idea of what I'm really speaking about. So let's figure out the slope, or not even the slope, but the calculation of what's happening. Let's look at where x is. Find it where the function, here's a point lying on the function, evaluate it at x, so that's f of x. And then now, let's calculate the slope of the tangent line and then find the equation of the tangent line. Or imagining it, I guess. We don't really have anything to calculate. Whoops, I'm trying myself to draw this. Let's draw it. There we go. So there we have our tangent line drawn. And what we're interested, instead of kind of using the idea of h or a sometimes, they talk about what happens if you're a little further away. So I'm going to exaggerate just so that we can see the idea. I'm just a little bit above x, so x plus, and what they like to use is this idea of, instead of h, they start to use this delta x. Same idea as what we've been dealing with. But that, if you remember, my friends, is the change in x. Usually we kind of see that in slope formula sometimes. So if I can kind of help you with this a little bit, let us look at the function. Let's find where we're at. I think I might have exaggerated too much. We'll go with it. Now I want to be a little closer. I apologize. You have erasers, right? There we go. Okay, let me make myself a little closer. And of course, I know you can view the book for a prettier example, but I'm really, yeah, sorry for you. I'm a perfectionist and I really want to make this drawing pretty, but it does help you see when you try to draw these yourself what's actually going on. So let's make ourselves a little bit closer. It's probably my function that I chose. I tried to make it a little too steep at the very end. There we go. I just wanted to get on the line, that's all. All right, much better. F of x plus, delta x or h, so we say. Okay. So what we're trying to understand, if you don't know what f of x is, there's no way we understand what f of x plus h is, or f of x plus delta x is. But what happens is you can approximate it. And if we're kind of playing with this, I'm looking at a couple of ideas. I'm looking at the change in x. So remember, this particular part right here, if I can, I'll play with it this way. If we look at how we are rising from one point to another, maybe I'll highlight it, that's a little nicer. So from here to here, what's that distance? Same distance down here. That distance happens to be delta x, or change in x, or h, as you know and love. And I want to look at a couple things. What is my slope of my tangent line? Well, slope of tangent line, if we're drawing this a little bit prettier, slope of the tangent line, we have the change in x. Slope triangle, anyone recognize that? Right here, slope triangle. Change in x, change in y. Well, again, that distance right there is called delta x. And we have our differential to help us out here. We should have our delta y. So let me kind of make sure we have this. Let's draw this picture a little prettier. So what do we call this? My apologies, sometimes I run out of colors, but here I go. So the difference between f of x plus delta x and f of x, using this same sort of idea, see if I can highlight that, maybe turquoise a bit. Oh no, that's gonna mess it up. I'll keep it in purple. So this distance right here, that's the differences in the y's. Well, differences of the y's over differences of the x's, there's that slope coming back. We have our delta y right here. So that purple part, delta y. There's no way to compute this directly if we don't know who f of x is. And that's kind of the main portion around this. And you're like, why wouldn't we know who f of x is? Well, sometimes we have to approximate it, and that's where the previous section came in. So what I want to play with is, let's look at what's happening with the tangent line. So this is what we're looking at in terms of when you calculate the slope. They want to play with, or bring our attention to, the y value change based on the tangent line. So if I can do this in, I am running out of colors, so I can try this in purple a bit, purple highlight. So from here to here, and if I can draw that on the line, maybe I'll also use a red dot just to kind of help you see. We have something right here. Again, kind of looking at this distance right here. That, my friends, if you're relating it to slope of tangent line, is actually what dy is. So they're trying to kind of give us an idea is that these two values are pretty close. There's no way of figuring out what this part is if you don't know what f of x is, but you can approximate it based on your differential. I paused there because sometimes I lose people at this point. But take a look, maybe try to redraw these in your mind. Maybe try a different curve to kind of play around with it, or maybe there could be, maybe there's a nice little application in Desmos I can find for you. I'll think about it. So let's kind of rephrase just so that we know. I know you get stuck in the theory sometimes, but we'll give you a concrete example in a second. Let's remind ourselves. We've got the point of tangency. In our case, the point of tangency is x, f of x, according to our drawing. Remember that the slope of the tangent is the derivative f prime x. And also, look at the other idea, the slope of a tangent. What's the Leibniz notation for f prime x? dy dx. And in our picture, what they are trying to say one more time, that our delta x, oh, let's write this out, right? Our delta x part is actually equal to our dx part in the picture. See that yellow highlighting part right there? So the x value, the change in x's on your slope of your tangent line is the same as your delta x based on your change in the function. So that's kind of the part we're trying to get you at. So this is happening in the picture above. And so if we are really close for small values, of delta x, or sometimes we say h, we can finally approximate the difference of the y's, change in y, with using our dy. Separable. Let's see if I can write that in there now. So this is where it kind of brings back a little bit of the idea of linearization. We're trying to approximate functions here. We finally run into our conclusion that the differential is approximated with your derivative, slope of the tangent line, times dx. So sometimes you're like, well, great, I see a picture, I kind of get it. It has to do with relating the change in points from slope of tangent line with change in points to slope of what's actually happening on the actual curve. But how does this relate to an example we might see? And that's probably gets you a little bit more of a better idea. Give yourself some time, of course. But maybe sometimes seeing it in a concrete version kind of makes the idea go back a little bit nicer. So example 4, they are looking at giving us a function. It's a cubic function. They want us to find delta y and dy as x increases from 2 to 2.05. So the first thing I want to understand is I see that 2 and 2.05 are pretty close together, and that's what they're getting to talk about with the x's. So if you're trying to maybe label that for yourself, this is our x. Our x plus delta x is 2.05. So what does that help us out with that tells us that our delta x should be equal to dx. We know that that's happening when we wrote our picture from the previous idea. What's the change from 2 to 2.05? It's 0.05. So that might be helpful to start off with just analyzing what's happening on the x-axis. And then kind of think about what are we trying to find? We're trying to understand the dy and the delta y. So let's play with this a little bit. Let's look at a couple things. Let's look at the derivative of the function. Sometimes, you know, that's the most exciting part to calculate. So we have f prime x, nice polynomial, thank you. So we have 3x squared plus 2x minus 2. And then now if we're looking at our x value, what is our f prime at 2? We'll kind of use a different color to help you out. So we have 3 times 2 squared plus 2 times 2 minus 2. Do a little math. 2 squared is 4, 3 times 4 is 12, plus 4 minus 2, we end up getting a 14. All right. So at least we have kind of the slope of the tangent line at that point. And we'll piece it all together in a second. So let's talk about what's happening at our tangent line, because we just kind of defined the dy part. So let's go back. And let's look at what's happening along the tangent line. I could take this in any order, but sometimes it's helpful to relate it to something that we're not, how do you say, we didn't just learn right away. So remember, if we're going to play with what's happening along the tangent line, we have dy is defined as f prime x dx. So we could actually calculate it based on what we know already. In our case, our f prime of x, in our case it's 2. And our dx, in this case, is 0.05. So again, if we calculated f prime of 2, you'll notice that, oh, okay, we got 14. 14 times 0.05. A little bit of a math, we get 0.7. So we just calculated the dy part. So this is happening along the tangent line. So cool. At least we got that part. Now let's talk about what's happening along the curve. That tends to be a little more confusing for you because curves are, of course, more complicated than lines. I get it. So along the curve, what they're trying to talk about is what's happening at delta y. Let's write this a little prettier. There we go. And if you think about it, if you go back to our picture, delta y, I'm going to go back. Delta y is the value of the function at the end. So that would be if we were looking at whatever this value is, minus the value of the function at the beginning, all based on x and x plus delta x. If we play with it, if I'm playing with my function, perhaps maybe a quick sketch might help. I don't really know what the function looks like, but I can play with the 2 and the 2.05. And I can play with, well, if whatever the function happens to look like, you know, have some fun, draw it, whatever it looks like, maybe a little more. You can figure out what's happening on the y-axis, f of 2, and what's happening a little bit over on the y-axis when you calculate that function. So, differences of the y's, remember slope? So differences of the y's. We have the f of 2.05 and f of 2. And that should make sense because, well, I don't know, we played in algebra. This kind of goes like the y2 minus y1 in your slope formula, maybe. Maybe that could kind of help you connect it to something you already have learned. Sometimes it seems like it's abstract, but they're just having you look at it a little different way. So what we have to do for ourselves is figure out what's the function evaluated at 2.05 and the function evaluated at 2. And yeah, I could plug it in. It's not too horrible, but maybe I'll use my TI. No, we'll go. I mean, we have to use the TI anyways, but I'm trying to say, is it going to cause me more issues to actually do the calculation, or do I want to guarantee my accuracy? And I think I'll go with guaranteeing my accuracy. I know we can directly plug things in calculator, calculate with decimals, but it might be useful. Not to graph it. Sorry about that. Here we go. I might be interested in maybe an accuracy here. So if I want to type in my function one more time, might be nice. I have x cubed plus x squared. I'll modify what I had my previous function on. So x cubed plus x squared minus 2x plus 1. And you know me, I've been a fan of the table feature, especially if I have to compute decimals with cubes and all. Just double checking I entered everything in right. So let's go to table. And now we can say what's happening at 2 and what's happening at 2.05. Might as well if we paid all this money for the calculator. Now, what's happening at 2, that's a nice 9. I would like to point out, sometimes you can't see everything. So when you're at 2.05, scroll over to the actual y value and you see how sometimes the table cuts off values. So I try to use my exact value that I see below. I just want to make sure you're clear with that. So let's go back. Yeah, that's a lot nicer than trying to compute the decimals. What are we thinking? This is calculus. Let's save our brain power for these differential issues. Okay, so f of 2.05, let's remind ourselves. I had to go consult my calculator. That was 9.717625. Subtract off f of 2, and that was a 9. So now we get this decimal, 0.717625. And we have, actually, we have just calculated our delta y. And the idea behind this whole differential business here is to kind of play around with, if you compare these values, dy versus delta y, check it out. They are very close. Got so excited I shook the computer there. So little note, fairly close. See, so excited. Shaking the computer all over. Can't contain it. So that's what they're trying to describe here. Sometimes not seeing the concrete example. It's true. Delta y and dy are fairly close. When you look at the little difference between what we're seeing right here. As long as you're pretty darn close to x when you start off with. That's been the theme of this class anyways. For very small values away from x values, how does that affect the y values of the function? So think about that. So example 5, we've got the radius of the sphere to be 21 centimeters with a possible error of 0.05 centimeters. So finally, a concrete example. to kind of apply our differentials to. We're going to use these differentials to approximate maximum error. So that's a little more exciting. You know, why are we doing this in the first place? When we use this value for the radius that we're trying to understand to compute volume of the sphere. So if you change the value of the radius, what happens to the volume of the sphere? Are we really far off? Are we pretty close? Let's see. So let's kind of relate ourselves. Radius of the sphere was measured to be 21 centimeters. Okay. And we have possible error of 0.05 centimeters. So when people say possible error, what we're looking at is a plus or minus. It could be a little bigger. It could be a little bit smaller. So if we're talking about the actual radius, when you play around with what's being produced, the actual radius, excuse me, is 21 centimeters plus 0.05 and 21 centimeters minus 0.05. So we have actual radius varies from 20.95 centimeters to 21.05 centimeters. And is this a big deal? I mean, sometimes to the human eye, we might not be able to tell, but does it affect what's happening to the ball or the sphere, I guess, if we're talking about it this way? So the first thing you kind of want to play with when you're dealing with these ideas of differentials is, can we name who our delta x is? And so one thing we have to be careful about is we're not in terms of x's and y's, we're in terms of v's and r's. So this is where we kind of have a little change of scale. Change of coordinates, sorry about that. So remember, I know you're used to x, y. Just kind of think of how the function is set up. The independent variable is the radius. The dependent variable is the volume. So that's going to help us understand what we're trying to figure out. So differential. So we know r is 21 centimeters. And if we're talking about our differential, delta r, they're giving us the 0.05 centimeters. And we do know, according to our pictures, that anytime you find delta r, the difference of the x's, that is the same thing for very close values of x to the original x. That should be the same as dr. So just so that you want to keep in mind. Note to self. So remember, volume is a function of the radius. So when you do use the notation for these, we have to be careful. Okay, so let's play. Let's talk about differentials a little bit. Let's remind ourselves what is the formula, or what helped us a little bit. So they want us to find how much the volume is changing. So that's where we're looking at what is change in V. Here we go. All right. Now, if we have very, very close values to our original radius of 21 centimeters, which is what we're assuming to be, this change in V should be relatively close to our dV. And that formula is found by taking the derivative of the volume with respect to r multiplied by dr. So let's see what we can find. Well, we already know what dr is. Dr is 0.05 centimeters. We would have to calculate the derivative of volume with respect to r. That's the next thing we have to go with. So remember, volume is a function of r. So sometimes I'll rewrite it after I made my change of coordinates. kind of helps me understand this. Usually has to do with calculating a derivative. And don't get too tied up on everything. You know, we have the 3 times 4/3. That's the 3's are going to divide out. We still have the pi. We have to subtract 1 off the exponent. So we have 4 pi r squared. Well, now we want to talk about not just v prime r. We want to look at the certain value of r. So what I'm looking at, I got it. But r in my case was 21. So that would mean let's plug in that 21. 4 pi times 21 squared. And if we want to be exact, let's keep pi in the situation until we actually have to approximate at the very end. Don't cut off too soon. So 21 squared. I gotta punch that in. My brain is hurting right now. That's 441 times 4. So it's gonna be 1764. Sometimes the more calculus you do, the worse you get at some of the basic math. So I apologize. So we could actually have a value when we're calculating the volume, the derivative of the volume with respect to r evaluated at r equals 21. Should now be 1764 times pi. Multiplying that by the 0.05, the dr. I'll get, in terms of pi, I have 88.2 pi. Remember, volume is in terms of cubic units. And that would make sense because we had a centimeter here. And when we squared our 21, we had centimeter square here. So that gives you cubic centimeters. And then if you're trying to help you understand, you know, sometimes you can't picture when you're speaking about terms of pi. This is where it would be a little bit more nicer if we approximated. Let's have our brains think about what number we're getting. So again, I'm plugging in pi in terms of not plugging in, but using the pi button on my calculator. I'm getting approximately 277 I'll just say 0.9 cubic centimeters. That gives me an idea. And so what this tells us, if the radius is off, by, what do they say, 0.05 centimeters? The volume can be off by about 277 centimeters cubed. And you know what? That sounds like a lot. And if I had a way to draw a worried emoji, I could, or I would. Should we be worried? I mean, it does sound like a lot, you know, if we have those small values. Well, let's find out. Should we worry? Or maybe we have a calculation of how worried should we be? So this kind of goes into play with, you know, when you manufacture materials, there is always an error somewhere here and there based on the settings of the machines, types of materials used. And there's a point in terms of safety or so that they say, oh, it's okay, it's a lot. It won't hurt. It won't hurt the final result. And you might care a lot more, you know, not the fact that if we're making, you know, basketballs or so, but there is still a very, very important industry that cares that all the sizes are standardized. But maybe if these are parts that are, you know, making, you're actually using this to build your car or build the airplane that you're riding on. It does matter if the final result ends up being a little far off. And then there's a calculation of how worried should we be. So, you know, yes, I'm always worried about being off. This is where we get into relative error. And that's probably to me, I feel like that is a bit more useful in terms of the application. And sometimes if you are worried about relative, in our cases, depending on, sometimes we think about the difference from 1 to 100 is a lot. But then if you're speaking about 4 million, that's a very small difference. So this is where we're going to play with relative error. And it's also known as, just in case, people call it percent error sometimes. Sometimes that makes a little more sense when you're trying to memorize everything. So what this means, percent is always what? The part over the whole. So if we want to calculate the relative error for the volume, i.e. how worried should we be? That would be the differential over the original volume. And remember, we're approximating because we don't really know the changes in volumes for all those balls, I guess. I keep saying sphere, so I'm thinking of a ball. So we know that the differential change in V can be approximated by dV, and we could divide it by V. So we already figured this out, at least the top part, 88.2 pi. If you want to write in the cubic centimeters, no problem. What we'd be interested is understanding who's V. Remember, V is the volume evaluated at the actual radius, maybe of the settings. So I plug that into my volume formula. 21 cubed, yeah, who knows that off the top of their head? Well, some people do, actually. Professor Damien, one of my mentors, he can cube and square things in his mind. Okay, so 21 cubed multiplied by 4, 37044 divided by 3. That's going to give us 12348, and then we still have the pi, cubic centimeters. So that's what I'm writing up here, 12348 pi cubic centimeters. And see what happens? The units divide out, so do the pi's. So if we actually, let me move this over. Got a little excited calculating the V, but I didn't leave enough room for my result. So let's find this percentage. 88.2 divided by 12348. It's a long number, but let's go with it. 0.00714 approximately. That's a decimal form. If you convert to a percent, even that comes back to haunt us. That is approximately, moving the decimal over, 0.714%. So what does this mean? This is how far we're off from the volumes. If we change those radiuses or radii to be something within 0.05 centimeters. So my question, should we be worried? This is less than 1%. And so I'll let you decide. It does depend on what you're manufacturing. It could make a difference, but your volumes, what they're trying to say is if your radius is off by 0.05 centimeters, the relative error means the volume's off by about 0.714%, less than 1% off. So again, I'll leave that up to you. And depending on what you're manufacturing, the answer could be yes or could be no. But if I'm just talking about a sphere in calculus class, and I have no application to what this sphere is applying to, am I using it for something? I'm not too worried at this point. Hang in there, Math 170. I'll see you next section.